Hello. Today, we're going to dive into a powerful concept in precalculus, the composition of functions. This lesson is from AP Precalculus, topic 2.7, which is all about how to put functions together to create new ones. By the end of this video, you will be able to evaluate, construct, and decompose composite functions. That's right, we'll learn to calculate their values, build them from simpler parts, and break them down into those same simple parts. Think of it like assembling and disassembling a toy with Legos. So, let's get started with our first objective, evaluating compositions. Our first objective is to understand how to evaluate composite functions. A composite function is essentially a function inside another function. It's a way to combine two functions into a new, single function. Let's look at the formal notation and definition. We write it as f composition g of x, or f of g of x. This notation means that we first apply the inner function g to our input x. Then, the result of gx becomes the new input for the outer function, f. In other words, the output of the inner function, g, is used as the input for the outer function, f. It's a sequential process. A key thing to remember about composite functions is their domain. For the composite function f gx to exist, two conditions must be met. First, x must be a valid input for the inner function g. Second, the output of gx must then be a valid input for the outer function f. Let's put this into two steps. The domain of f gx includes only the inputs x that satisfy two criteria. First, x must be in the domain of g. And second, the output gx must be in the domain of f. Both conditions are necessary. Now, let's practice evaluating these compositions. We'll start with a numerical example. This means we'll plug in a specific number for x. Consider the functions f of x equals 3x plus 1 and g of x equals x squared. Let's find f of g of 2. Our goal is to calculate the value of the composite function f gx when x is 2. The rule here is to always evaluate from the inside out. This means our first step is to calculate the value of the inner function g of 2. We substitute 2 into gx. Since g of x is x squared, g of 2 is 2 squared, which equals 4. Now, this result, 4, becomes the input for our outer function, f. So, our second step is to evaluate f of the result we just found, which was 4. Since f of x is 3x plus 1, f of 4 is 3 times 4 plus 1. That's 12 plus 1, which gives us 13. Therefore, f of g of 2 equals 13. We followed the two-step process. Find g of 2, then find f of that answer. What if we did it the other way around? Let's find g of f of 2. First, we evaluate the inner function, f of 2. This is 3 times 2 plus 1, which is 7. Now, we use 7 as the input for the outer function, g, so we find g of 7, which is 7 squared, or 49. Notice that f of g of 2 was 13, but g of f of 2 is 49. This demonstrates a crucial property. Function composition is not commutative. The order matters. We can also evaluate compositions when functions are given to us graphically. This means reading the values directly from the graphs of the two functions. Imagine you are given the graphs of a function f of x and a function g of x. Our task is to find f of g of negative 3. Here are two graphs. Let's say the red one is g of x and the blue one is f of x. We need to find the value of the composite function at x equals negative 3. Just like before, we start with the inner function, in this case g of negative 3. So, our first step is to find g of negative 3. On the graph of g of x, when the input x is negative 3, we look up to find the corresponding y value on the red curve. Let's say that value is 4. Now, we use this output, 4, as the input for our outer function, f. This is our second step. Find f of 4. We now look at the blue graph, f of x. We find the point on that curve where the input x is 4. Let's say the corresponding y value on the blue curve is 2. Therefore, the composite value f of g of negative 3 is 2. The graphical method follows the exact same inside-out principle. We've covered numerical and graphical evaluation. Now let's move on to our second major objective, constructing composite functions. This means starting with two functions and building their formula, like using algebraic expressions. The process for this is a direct extension of what we've already done. To construct f of g of x, we substitute the entire expression for the inner function g of x for every instance of x in the outer function, f. Let's work through an example. Let f of x equal x squared plus 1 and g of x equal 3x minus 2. We want to construct f of g of x. Step 1 is to identify the outer and inner functions. Here, f is the outer function and g is the inner function. Step 2 is to take the entire expression for g of x, which is 3x minus 2, and substitute it everywhere we see an x in the formula for f. The formula for f of x is x squared plus 1. When we replace x with the quantity 3x minus 2, we get the quantity 3x minus 2 squared plus 1. Now we just need to simplify this expression. First, we expand the squared term. 3x minus 2 times 3x minus 2 gives us 9x squared minus 12x plus 4. We then add the plus 1 at the end. Combining the constants, 4 plus 1 is 5. So the final simplified composite function is 9x squared minus 12x plus 5. We have successfully constructed the composite function. Remember what we said about order? Let's prove it by constructing g of f of x with the same two functions. This will show us that composing functions in the other order yields a completely different function. This time, g is the outer function and f is the inner function. So, we substitute the expression for f of x, which is x squared plus 1, into the formula for g. The formula for g is 3x minus 2. Replacing the x with x squared plus 1, we get 3 times the quantity x squared plus 1 minus 2. Now we simplify. Distribute the 3x squared plus 3, then subtract 2. The final result is 3x squared plus 1. This is clearly a different function than the one we found for f of g of x, which was 9x squared minus 12x plus 5. This confirms that composition is not commutative. The function you get depends entirely on the order in which you compose them. There is one special case where the order doesn't matter. This happens with the identity function. The identity function is defined as f of x equals x. It's the simplest function imaginable because whatever you put in, you get out. If you compose any function g with the identity function f, you get the function g back, in both orders. The identity function acts like the number 0 for addition, or the number 1 for multiplication. It leaves the other value unchanged. We've learned to evaluate and construct composite functions. Our third and final objective is to learn how to do the reverse. Decompose a complex function. This means we start with a function that looks like a composition, and we want to find the two simpler functions, an inner and an outer function, that were used to build it. This might seem tricky at first, but with practice, you'll get the hang of it. The key is to look for an inner operation or expression inside a larger outer operation. The strategy is to identify the last operation that would be performed according to the order of operations. That is often your outer function. Then, the part inside that last operation is your inner function. Let's try decomposing f of x equals the quantity 3x plus 2 raised to the 4th power. This function clearly looks like a composition. What is the inner operation happening? The core, the piece that's plugged into something else, is the linear expression 3x plus 2. So, we can define our inner function, g of x, as 3x plus 2. Once we identify the inner function, we replace that entire part of the original expression with a simple x to find the outer function. If g of x is the part inside the parentheses, then our outer function, h of x, is simply x to the 4th power. Let's check our work. If we compose h of g of x, we get h of 3x plus 2, which is 3x plus 2, to the 4th power. This matches our original function, f of x. We have successfully decomposed the function. Let's try another one that involves a transformation. Decompose f of x equals the square root of x plus 5. Here, the inner part is the expression inside the square root. The inner function, g of x, is x plus 5, and the outer function, h of x, is the square root of x. Again, we've broken it down into simpler components. Understanding decomposition is also the key to understanding transformations of functions. Any transformation, whether it's a translation or a dilation, can be thought of as a composition. Let's consider a vertical translation. If we start with a function f of x and we want to shift it up or down by k units, the transformed function g of x is equal to f of x plus k. This is a composition. The inner function is g of x equals f of x, and the outer function is h of y equals y plus k. We are inputting the function f of x into the adding function h. The same principle applies to dilations, or stretches and compressions. A vertical dilation, where we multiply the whole function by k, is a composition of f with a scaling function. Similarly, a horizontal dilation, where we multiply x inside the function, is a composition of a scaling function with f. Decomposing functions into these simpler inner and outer parts makes it much easier to analyze complex functions and understand their behavior on a graph. Let's quickly recap what we've learned about the composition of functions. First, we learned the definition of a composite function, f of g of x. It's a function inside a function, with the output of the inner function becoming the input of the outer. Second, we practiced evaluating these functions using numerical values, algebraic expressions, and even graphical representations. Third, we saw how crucial the order is. Function composition is not commutative. F of g of x is usually not the same as g of f of x. Fourth, we learned to construct composite functions by substituting one function's expression into another. And finally, we learned how to deconstruct functions, breaking them down into an inner and an outer function, and we saw how this concept is related to function transformations. You now have the tools to work with compositions from multiple perspectives. The key is to practice identifying that inner and outer relationship. Keep practicing, and you'll become a master of functions inside functions. Thank you for watching.